Hey there, and welcome. Have you ever just looked at a number and thought, it's just a number? Well, today we're going to pull back the curtain because it turns out every single number has a secret identity, a hidden code that defines literally everything about it. So, what is this secret code? How can a simple number like, say, 12 or 30 have a secret message locked inside of it? That's exactly what we're about to find out. Let's start by looking at what makes up a number's most basic identity.
All right, so the first clue to cracking this whole thing lies in what I like to call the DNA of numbers. Yeah, you heard that right. Just like living things are built from these tiny biological components, numbers are built from something just as fundamental.
And here it is. This is the key to everything. The fundamental theorem of arithmetic. It's a fancy name, but the idea is actually pretty simple. It says that any number you can possibly think of, well, as long as it isn't already a prime number, can be broken down into a totally unique set of primes. These primes are like the atoms, the absolute rock-bottom building blocks of the entire number universe. And here's the really mind-blowing part. That breakdown isn't random. Not at all. It's a unique fingerprint. The number 12 will always be 2 times 2 times 3. That's it. Nothing else. No other number in the universe shares that exact same prime code. It's a perfect, unchangeable identity. So now that we know this code exists, what can we actually do with it? Well, this is where it gets really, really cool. Once you understand a number's prime DNA, you can suddenly see exactly how it relates to every other number out there. Let's just take two simple numbers to see how this works, 6 and 20. The prime code, or its prime factorization, for 6 is super easy. It's just 2 times 3. For 20, it's 2 times 2 times 5. We can see their building blocks laid out right there. Now let's see what this actually helps us do. These codes make finding things like the highest common factor and the lowest common multiple, well, honestly, a piece of cake. The HCF is just built from the prime blocks they both share. For the LCM, you just take the biggest set of blocks you need to build both of the numbers. It's that simple. And this slide just lays it all out. To find the HCF, we look at their codes, 2 times 3 and 2 times 2 times 5. What's the only building block they have in common? Just a single 2. That's it. That's our HCF. For the LCM, we gather all the blocks we need. We need 2 2s from the number 20, we need 1 3 from the number 6, and we need 1 5 from the number 20. You multiply those all together, and you get 60. Now, what's really just beautifully elegant about this is that these two values are connected by this amazing formula. For any two positive whole numbers, if you multiply their HCF and their LCM, you get the exact same answer as multiplying the two numbers themselves. Let's put it to the test with our numbers, right? The HCF was 2, the LCM was 60. Okay, 2 times 60 is 120. And what's 6 times 20? Also 120. See? It works perfectly. Every single time. But just when you think you've figured out the rules of the universe, you discover that some things, they just don't play along. It turns out, not every number can be neatly broken down into a prime code. These are the rebels, the outliers. So, meet the irrational numbers. Their whole deal is that they completely defy our system of fractions. You can't capture their true value by dividing one whole number by another. They exist outside of that nice, orderly world we were just talking about. You know these numbers. Think about the square root of 2, or pi. Their decimals just stretch on and on into infinity without ever falling into a repeating pattern. They are the beautiful, unpredictable glitches in the mathematical matrix. Okay, so how in the world do you prove something is infinite? How can you be 100% sure a number's decimal will never, ever repeat or just stop? You obviously can't watch it forever. So instead, you have to set a really clever logical trap. And the tool for this job has this awesome name, proof by contradiction. This strategy is brilliant. You start by assuming the exact opposite of what you want to prove. You just pretend the number is rational, that it plays by the rules. And then you follow that logic until it completely falls apart. So here's how we set the trap for the square root of 2. We start by assuming it's not a rebel. We say, okay, let's pretend you're a normal, rational fraction, r divided by s, and let's say this fraction is as simple as it can possibly get. Then, after a little bit of algebra, our assumption leads us to a strange conclusion. The top number, r, has to be even. But this is where the trap gets really interesting. If we follow that logic just one step further, it proves that the bottom number, s, also has to be even.
And right there, that's it. That's the trap springing shut. That is the contradiction we were looking for.
So why is that a contradiction? Well, remember back in step 1, we insisted that our fraction r over s was in its simplest form. But if both r and s are even, you could obviously simplify it further by dividing both of them by 2. We literally just broke our own rule. And the only way for that to happen is if our very first assumption that the square root of 2 is rational was completely, totally wrong to begin with.
So what have we actually discovered here? We found that the world of numbers isn't just one big happy family. It's actually split into two very, very different realms. On one side, you have the rational world. It's orderly, it's predictable, these are numbers that can be written as fractions, and they all have their own unique prime code. And then, on the other side, you've got the irrational world. Infinite, mysterious, and absolutely impossible to pin down with a simple fraction. Okay, so to make sure we've got a good handle on that orderly, rational world, let's try a quick puzzle. Take a look at this expression. Without even calculating the final number, how can we know for sure that it's composite? In other words, that it's definitely not a prime number. The answer is hiding right there in the structure. Both parts of the sum share a factor of 13, so you can just factor it out. This proves the entire number is divisible by 13, and since it has a factor other than 1 in itself, it cannot be prime, it has to be composite. See? It all comes back to factors. So the next time you use a number, just remember this. You're actually stepping into one of two parallel worlds. One is built on these finite, unique codes, and the other just stretches out into this endless, unrepeatable mystery. And that kind of leaves us with a final thought. If something as basic as a number contains these two completely opposite universes of order and chaos, what other simple things that we see every single day are hiding a secret, complex world just beneath the surface? Thanks for tuning in.